Imagine yourself gazing up at a starry night sky. You find yourself standing on a spinning planet, hurtling through space at unimaginable speeds. Yet from your perspective, the world seems perfectly still. This is the essence of a reference frame, our unique viewpoint within the vast expanse of the universe. In physics, a reference frame is a coordinate system that we use to describe the motion and position of objects. It's like a grid superimposed on the universe, allowing us to pinpoint the whereabouts of things relative to a specific observer. Your chair, for instance, might be at rest with respect to the floor of your room, but it's in motion relative to someone observing from a speeding train. The concept of reference frames is crucial for understanding motion and its relativity. When we describe the motion of an object, we implicitly do so from a particular reference frame. Whether an object is at rest or in motion depends entirely on the chosen reference frame. This idea might seem straightforward at first, but it has profound implications for our understanding of space and time, as we'll soon discover. Understanding reference frames is the first step toward unraveling the mysteries of relativity. Long before Einstein revolutionized our understanding of space and time, the foundations of classical physics were being laid by great minds of the past. One of the most influential of these early thinkers was Galileo Galilei, who laid the groundwork for classical physics with his principle of relativity. Galileo's work was pivotal in shifting the perspective from a geocentric view of the universe to a heliocentric one, challenging the long-held beliefs of his time. Galileo's insights, rooted in observations of everyday objects, formed the bedrock of our understanding of motion for centuries. His experiments, such as those involving inclined planes and pendulums, demonstrated that objects in motion remain in motion unless acted upon by an external force. Galilean relativity at its heart states that the laws of motion are identical in all inertial frames of reference. This means that whether you are on a moving train or standing still in a park, the fundamental principles governing the motion of objects remain the same. An inertial frame is one that is not accelerating. Think of a train moving at a constant speed on a straight track, or a spaceship coasting through the void. In these frames, the behavior of objects can be predicted with great accuracy, using the laws of classical mechanics. Within these frames, the laws of physics remain consistent. This consistency is what allows scientists to conduct experiments and make predictions about the natural world. It is the cornerstone of classical mechanics and has been instrumental in the development of technology and engineering. This principle implies that there's no absolute state of rest. In other words, there is no single privileged frame of reference in the universe. Everything is in motion relative to something else, and this relative motion is what defines our experience of space and time. A passenger on a smoothly sailing ship, for instance, would observe the same laws of physics for a ball tossed in the air as someone standing on solid ground. This observation underscores the universality of the laws of motion and their applicability in different contexts. The ball's trajectory may appear different to observers in different frames, but the underlying physics governing its motion remains constant. This concept is crucial for understanding how different observers can perceive the same event in different ways, yet agree on the fundamental principles at play. For centuries, Galilean relativity reigned supreme, providing a reliable framework for understanding the motion of objects in our everyday world. It was a paradigm that explained everything from the fall of an apple to the orbits of planets, and it stood unchallenged for a long time. However, the advent of special relativity would reveal that at speeds approaching the speed of light, the classical view of space and time would no longer hold sway. Einstein's theories would revolutionize our understanding, showing that space and time are interconnected and relative, fundamentally altering the way we perceive the universe. As physicists delved deeper into the nature of light and electromagnetism in the late 19th century, they began to uncover phenomena that didn't quite fit into the established theories of the time. The scientific community, which had long relied on the principles of classical physics, found itself facing a series of perplexing questions. These questions would eventually lead to a profound shift in our understanding of the universe. Cracks began to appear in the seemingly unshakable edifice of classical physics. The once solid foundation of Newtonian mechanics and Galilean relativity started to show signs of wear and tear. The elegant and predictable world of classical physics was being challenged by new experimental data that couldn't be easily explained. Experiments revealed puzzling inconsistencies that defied explanation within the framework of Galilean relativity. These inconsistencies were not minor anomalies but significant deviations that called into question the very core of classical physics. Scientists were left scratching their heads, trying to make sense of the data that seemed to contradict everything they had known. One of the most significant conundrums was the behavior of light itself. Light, which had been studied extensively, was now presenting properties that were difficult to reconcile with existing theories. The wave-particle duality of light, its speed, and its interaction with matter were all areas of intense scrutiny and debate. Maxwell's equations, which elegantly described electromagnetism, predicted that the speed of light in a vacuum is a constant, regardless of the motion of the source or the observer. This was a revolutionary idea that challenged the traditional notions of how velocities add up. According to classical physics, if you were moving towards a light source, you would expect to measure a higher speed of light than if you were stationary. But Maxwell's equations suggested otherwise. This prediction clashed with the traditional way of adding velocities, where an observer moving towards a light source would expect to measure a higher speed of light than an observer at rest. This discrepancy was more than just a mathematical oddity. It hinted at a deeper, more fundamental issue with our understanding of space and time. The constancy of the speed of light suggested that our intuitive notions of motion and measurement were incomplete. This discrepancy hinted at a fundamental flaw in our understanding of space and time. It suggested that the very fabric of reality, as described by Newtonian mechanics, was not as straightforward as previously thought. The idea that space and time were absolute and unchanging was being called into question. Scientists began to realize that a new framework was needed to explain these anomalies. It suggested that the familiar notions of absolute space and time, as envisioned by Newton and reinforced by Galilean relativity, were not absolute after all. The concept of an unchanging universal clock ticking away in the background of the universe was being challenged. This was a radical departure from centuries of scientific thought and required a complete rethinking of the principles that govern the physical world. It was against this backdrop of scientific upheaval that Albert Einstein, a young patent clerk with an extraordinary mind, stepped onto the world stage, ready to reshape our understanding of the cosmos. Einstein's insights were not just incremental improvements on existing theories. They were revolutionary ideas that would change the course of physics forever. His work would provide the answers to the questions that had been puzzling scientists for decades. His theory of special relativity, published in 1905, would forever alter our perception of space, time, and the nature of reality itself. This theory introduced concepts that were both mind-bending and elegant, such as the idea that time could dilate and lengths could contract depending on the relative motion of observers. It was a paradigm shift that opened up new avenues of thought and experimentation, laying the groundwork for modern physics. At the heart of Einstein's groundbreaking theory of special relativity lie two simple yet profound postulates that challenged the very foundations of classical physics. These postulates, though seemingly straightforward, have far-reaching consequences that ripple through the very fabric of our understanding of the universe. These postulates, rooted in experimental observations and elegant in their simplicity, serve as the unshakable pillars upon which the edifice of special relativity is built. They are not just abstract concepts but are grounded in the meticulous work of scientists who came before Einstein and in the precise measurements and experiments that continue to validate them today. The first postulate, known as the principle of relativity, extends Galileo's principle to encompass all laws of physics, not just those governing motion. Galileo's insights laid the groundwork for this principle, which asserts that the laws of physics are invariant or the same in all inertial frames of reference. This means that whether you are on a moving train or standing still on the ground, the fundamental laws that govern the universe apply equally. It states that the laws of physics are the same for all observers in uniform motion. This principle is a cornerstone of modern physics, ensuring that the results of any physical experiment are consistent, regardless of the constant velocity at which the observer is moving. This universality is what allows us to make sense of the physical world, no matter where we are or how we are moving. This means that no experiment can distinguish between an observer at rest and an observer moving at a constant velocity. In other words, there is no preferred frame of reference in the universe. This idea was revolutionary because it contradicted the long-held belief that there was an absolute state of rest. a concept that had dominated scientific thought since the time of Newton. The second postulate, the constancy of the speed of light, is the truly revolutionary idea that sets special relativity apart. This postulate asserts that the speed of light in a vacuum is a universal constant, unaffected by the motion of the light source or the observer. This constancy is not just a curious fact, but a fundamental aspect of the nature of light and space-time itself. It asserts that the speed of light in a vacuum is the same for all inertial observers, regardless of their relative motion or the motion of the light source. This means that the speed of light is an absolute constant, a fixed value that does not change, no matter how fast you are moving or in which direction. This constancy leads to some of the most mind-bending implications of special relativity. This means that whether you're chasing after a beam of light or running away from it, you'll always measure its speed to be the same constant value, approximately 299,792,458 meters per second. This constancy defies our everyday experiences and intuitions, where speeds seem to add up or subtract depending on the direction of motion. Yet, it is this very constancy that leads to the remarkable phenomena of time dilation and length contraction. These two postulates, seemingly at odds with our everyday experience, have profound implications for our understanding of space and time. They force us to rethink our notions of simultaneity, causality, and the very nature of reality. The interplay between these postulates leads to the realization that space and time are not separate entities, but are interwoven into a single continuum known as space-time. They force us to abandon the Newtonian notions of absolute space and time and embrace a new reality where space and time are intertwined and relative to the observer. This new understanding has paved the way for modern physics, influencing everything from the behavior of particles at the quantum level to the dynamics of galaxies in the cosmos. The pillars of special relativity have not only reshaped our understanding of the universe, but have also opened up new avenues of exploration and discovery, forever changing the landscape of science.